So now that we are done and have really Stone-Weierstrass in its full generality and its beauty, maybe we should also just write down the corollaries which we get for the classical situations. I mean, in the classical situations, polynomials, and so it's very easy to check the assumptions, and so I mean they follow right away from this general version. Okay, so as a corollary, let me write this down, and we don't have to restrict to functions on R, but it could also be functions in R to the n. So let X be a compact subset of R to the n. Okay, and maybe as before I should call it K. And then I'm looking on the polynomials which are continuous functions on this set, and I look polynomials in the coordinate functions. Of course, I have the coordinate functions x1 up to xn, and I can take polynomials in them, and then those guys are dense in C of in the continuous functions of k. And it's very easy to check that those coordinate functions, the polynomials in the coordinate functions, really satisfy those assumptions. So what we get then from this is that the algebra of all polynomials, and of course it's a unital algebra because a constant polynomial is of course also part of this. So those are P of x1 up to xn in the coordinates. Coordinates. So this is dense in the continuous functions on k. And n equal to 1 is exactly the classical Weierstrass theorem. But general n is not harder here. It's classical Weierstrass theorem. Okay, then maybe another corollary which I also want to give is maybe one which goes more in the direction of Fourier analysis or trigonometric polynomials. So I mean, we only have to take a subalgebra, so we should take a set of functions which is closed under addition and multiplication. And it should be big enough to separate points. Okay, and trigonometric functions, polynomials, so I mean polynomials in sine and cosine have this property. And of course those are very important functions, and Fourier analysis relies partly on the fact that this actually is a big enough class of functions, namely it is dense. And this is also part of this. So I mean, let's say this is part 1, and part 2 is that if I take the set of all trigonometric polynomials, and with this I mean finite sums which are given in terms of cosine and sine. So polynomials, so this means finite sums of the form, so f of t is of course a constant should also be there, and then I take sums, finite sums, summing from 1 up to n. I have coefficients, and then I have cosine k times t plus bk sine kt. So I take the basic sine and cosine, and I take higher frequencies of this. So k is here arbitrary natural number. Okay, so this sums of this form, I mean they really form an algebra. If you multiply things like this, then you come back. And of course this depends on the fact that if you multiply two signs, you can write it as another sign. So this is the addition formulas for the sine of alpha plus beta. You can write this as a product of sines. Or the other way around, if you have a product of sines and cosine, you can rewrite this as a sine with a different frequency. Good. Okay. So this, you look on this, and those guys are uniformly dense, but of course, I mean, not in the space of continuous functions on R, because what you get here are functions which are periodic. So you really have to restrict things from continuous functions to functions which are periodic, and in this case, it's a period of 2 pi. I mean, all the functions which I have here, cosine and sine, have a period 2 pi, so it is clear that I can only approximate functions which are also periodic. And maybe, okay, maybe you say this doesn't really fit into this frame, because here I should have just continuous functions on something without any additional constraint. But the only thing one has to see is that functions which are continuous, 2 pi periodic continuous on R, that actually you can consider them as continuous functions on the unit circle. And then you really have continuous functions on the unit circle, and the unit circle is a compact set. Okay, so this is finite sums of this form is uniformly dense. Uniformly dense in the space of 2 pi periodic and continuous functions on R. Yeah, and of course, I mean, R is not compact, but I mean, if I have functions which are continuous with period 2 pi on R, as I said, this is the same as continuous functions on a unit circle, and this is continuous. Yeah, okay, so let me write this as C periodic on 0 to 2 pi. And of course, I mean, instead of saying on R, I can say on the interval from 0 to 2 pi. So this goes to R. It's continuous, and then periodicity means that f of 0 is the same as f of 2 pi. And so this is a subset of the continuous functions of 0 to 2 pi. Yeah, okay, but the point is, if you want to apply Stone-Weierstrass, you have to identify the continuous functions, the periodic continuous functions on 0 to 2 pi with the continuous functions on the unit interval. Because then the periodicity is part of the continuity in the unit interval. So maybe I should just write this down here, because that's a crucial point. So the periodic functions on 0 to 2 pi can be identified with the continuous functions on the torus, on the unit circle. And the unit circle, those are the elements in R2. Yeah, the unit circle x squared plus y squared is equal to 1. So this is a compact subset in R2. And this identification goes that you identify a t in this interval with, let's say, on the circle with cosine t sine t, or an element in R2. Okay, and then the trigonometric polynomials which you have there correspond to the polynomials in these coordinate functions here. Okay, so you have to make this identification, and then it's directly the Stone-Weierstrass. Good. Okay, and then maybe instead of going for more examples, maybe finally I also want to give you the complex version of Stone-Weierstrass. So I mean, here we have talked about C of k, which are the real valued functions, and in many situations we want to consider the complex valued functions. And of course, I mean, you can reduce this to this situation by going over to real part and imaginary part. So in principle, it is an easy consequence out of this. But of course, because your space of functions is bigger, you also need a condition on A which somehow respects this. Okay, and so maybe I just want to write down the statement. So, namely the complex version of Stone-Weierstrass, which is the one which we are going to use later, because if we are talking about Banach algebras, usually we will consider complex versions. Okay, but anyhow, but it's nothing new. It follows more or less directly of this. Okay, and so let me write down the statement. So again, I have a compact space on which I consider continuous functions. But now I consider continuous functions which go not to R, but to C. And in order to distinguish it from before, I denote this by C, K, comma, C, the complex numbers. So those should be the functions from K to C which are continuous. Yeah, okay, and again, I mean, I can take the subnorm on this, and then it becomes a Banach space, a complex Banach space. Above, I had a real Banach space. So this is equipped with the subnorm. Yeah, okay, now I consider, as before, a subset of those continuous functions, and I want them to be dense. And what are the conditions? Of course, I need, as before, that I have a unital subalgebra, and it should separate the points, but in addition, it should also somehow respect the additional mapping which I have in a complex setting, namely the complex conjugate. So I need this as an additional condition. Okay, so I consider A a subset of those complex valued continuous functions on K. So this should be, as before, a unital subalgebra. And now, of course, I can multiply my functions with complex numbers. And this should not lead out of so this subalgebra means I can also multiply with complex numbers, of course. And as before, it should separate points, which separates the points of K. Okay, but then I also need an additional property in a complex situation. So namely, if I have a function f in A, then the complex conjugate should also be there. Complex conjugate should also be in A. And complex conjugate is again pointwise. If I have a function which goes to C, I can define f bar as the function which at every argument takes the complex conjugate of f, of the argument. Okay, and whenever I have this, then actually I have the same statement as before, namely A is then dense in those continuous functions. So if I have this, then A is dense in continuous functions from K to C. And dense, of course, with respect to the subnorm. Good. Okay. So I mean the proof of this is easy, so I'm not going to do this, but it's good to have this statement because probably that's the version which we are going to use later when we do our Gelfand theory. Okay, so that's what I wanted to say about Stone-Weierstrass. So this is nice, important, and it will also be useful in what we are going to do later.